Hello, this is Kevin Smith, Audio Electronics, and I'm here to talk to you a little bit today about standing waves. Standing waves. Standing waves are when a frequency bounces off a parallel surface onto itself, creating all kinds of problems for audio environments. Nodes. Nodes are points of no motion in sound. So they're basically the meeting of a crest with a trough. So if you're standing in a node, that means that the sound's going to be a lot quieter. And sometimes they just occur randomly throughout the room, or other times they occur for specific reasons. Antinodes. They are positions of maximum amplitude, so it means that they are positions where sound is really loud in a room. And it's kind of like nodes, only the opposite. So, standing waves are bad because it means that if you're trying to record something, or if you're in a room trying to listen to sound, you might not get an accurate picture of what the sound really actually sounds like, because different parts of the room might you might experience the sound differently in different parts of the room, because when there are two parallel walls in a room, it creates all kinds of different audio problems, and it can just make for a difficult recording environment. So let's say you're working in a studio and you're trying to adjust the bass for a song. If you happen to be in a node for that particular frequency, then you're not going to hear the bass very well. So that means that you're going to keep turning it up, which by the time you make the final recording, it's going to sound completely wrong. So that's why we don't like standing waves. So let's try it hands-on. Okay, so I'm in this room right now that's really tiny. And I mainly chose the really tiny room because I'm measuring with this. Yes, so I went ahead and pre-measured, but I had to go along the wall and measure it one little 12-inch piece at a time. So I made a fancy diagram of the room. We have wall 1 is going to be the distance between this wall and the door. Wall 2 right here is going to be the distance between the edge of the door, or the corner of that, and the trash can over here. And then I did floor to ceiling. So that's going to be the floor to the ceiling. Okay, so, I missed a few. Oh, no, I didn't. Okay, so I went ahead and calculated, and I have wall number 1 was 330.5 inches, which translating it into feet is about 27.6 feet. Wall number 2 is 72 inches, or in feet that's 6 feet. And the floor to ceiling measurement was 86 inches, which is about 7.2 feet. So the calculation that one uses to find the frequencies within a room, or between two walls I should say, is frequency equals velocity over distance. So that is just, the frequency is what we're trying to calculate. We're trying to figure out what this frequency is that will fit between two walls. The velocity is going to be the speed of sound, which is, I have to peek because I can't remember, is 1,130 feet per second. And the distance is going to be the measurements that we made of the walls. So I went ahead and calculated it, and the first wall with 1,130 over 27.6, that is 40.9 hertz between this part and the floor over here. And the second wall was 1,130 over 6, which equals 188.3 hertz. So that's that corner in there, 188.3 hertz. And then the floor to ceiling is 1,130 over 7.2, which is 156.9 hertz. So that's floor to ceiling. Oh, yes. And that is the end. Those are the calculations that I made for this tiny little room in College Avenue. And so if you are ever happen to be crazy enough to decide that you really want to monitor really good audio inside College Ave, don't come to this room because everything's parallel. It's a giant box. Okay, so thank you for listening. This has been Kevin Smith's lecture on audio electronics. Thank you and good night.